Hello, folks. We are going to continue on in Chapter 4. We go to 4.3 next. We do not do 4.2. So it is the remainder and factor theorems. The remainder theorem is written for you on the screen right now. It says if a polynomial p of x is divided by x minus r, the remainder is a constant p of r, and p of x equals x minus r times q of x plus p of r, where q of x is a polynomial with degree 1 less than the degree of p of x. Naturally, right? This is clear as mud. That's a lot of math speak all in one. So what I want to do is use an example to kind of illustrate what this means. All right, this is a problem that we could work on that relates to the remainder theorem, shows or demonstrates it. It says let p of x, the polynomial, be 2x cubed plus x squared minus 4x plus 3. Show that p of negative 1 is the remainder when p of x is divided by x minus or x plus 1. So what are we doing here? Well, let's look at what it's asking us to do. It wants us to divide p of x by x plus 1. So let's do that first. All right, let's do that division first. So I'm going to use synthetic division, and let's just use a color here. So let's do 2, 1, negative 4, and 3. And if I'm dividing by x plus 1, then in the box would go negative 1. And I would have this. So we have this. Now we would bring down the 2, multiply by negative 1, add. We get negative 1, multiply by negative 1, we get 1. Add to negative 4, we get negative 3. Multiply by negative 1, we get 3, and 6 is left over. That's our remainder. So our quotient for this, let's see. No, I had it right the first time. All right. Our quotient is, whoops, let me write it out. Quotient is 2x squared minus x minus 3 and plus a remainder of 6, which we would put over x plus 1. All right, so that is our quotient. So I want you to key in on this number. This, whoops, let's get rid of that. All right, this number here, that remainder of 6. They asked us to divide by x plus 1, but they also said show that p of 1 is the remainder. All right, p of negative 1, I should say. So what they're saying is in the original function, which was our p of x, again, just to write this down again, was 2x cubed plus x squared minus 4x plus 3. And they are saying in that original statement, they want us to find p of negative 1. So to find p of negative 1, we plug in negative 1. So 2 times negative 1 cubed plus negative 1 squared minus 4 times negative 1 plus 3 is what we're looking for. Negative 1 cubed is negative 1 times 2 is negative 2. Negative 1 squared is 1. Negative 4 and negative 1 multiplied is a positive 4. And then we have plus 3. So we're adding 8 to negative 2. That would give us 6. Notice it said let p of x be this. Show that p of negative 1 is 6, is the remainder when p of x is divided by x plus 1. So what we notice here is when we do the division by the factor related to the root negative 1, we get the same thing as plugging in the root. In other words, the value of the function is the remainder of the division by the factor. All right, now think about that again. The value of the function at any point, the y value for the function, is the remainder when we divide by the factor created by that. All right, so let's look back at this again and take a look at what we have here. If p of x, all right, so we did p of x was red. P of x is this thing here, right? P of x is this. If p of x is divided by x minus r, our x minus r was already highlighted in green here. That's that. X minus a negative 1. Negative 1 is our r, so x plus 1 is our factor, right? So it's divided by x minus r. And the remainder is a constant, p of r. The remainder was a constant. It was 6, right? So the remainder is 6. And p of x, the polynomial, can be recreated by doing x minus r times q of x. Now, q of x was that quotient. That was this thing down here, right? So what it's saying is if I took this 2x squared minus x minus 3, and multiplied it by x plus 1 and added 6, I would get my original polynomial. That's what this is saying. X plus 1 times that quotient plus the remainder would give us back our polynomial. All right. Now, what does that mean to us? We kind of know a little bit how all this works. So why is this important to us? So let's look at an example of what they could ask us and why we can use this so effectively. All right, it says use the remainder theorem. So again, it's saying use this remainder theorem to find the remainder for the division and then state whether the binomial is a factor of the polynomial. Now, there's two things here. One is something new, something old is the state whether the binomial is a factor. We know it's a factor if it goes in evenly. That was from the previous section, right? That's from 4.1. But use the remainder theorem to see if it actually does go in. Instead of having to do the division to find out whether it's a factor, we can use the remainder theorem. Now, what that means is this. It's easier to plug in. This would be r is equal to 2. The root is 2, right? Because x minus r is the standard form for this. So r is 2. Instead of having to divide what would be 2 into this whole thing, we can just plug it in. We can do p of 2 equals 2 cubed minus 2 plus 6, right? Just plugging in 2 because we want to find the function value, this thing's value at 2. So that would be 8 minus 2 plus 6. So that is 12. So that being 12, that is our remainder, right? This is using, by the way, when it says use the remainder theorem, this is what we'd expect to see. If you do the division, you're not going to get credit for it, all right? When you are given specific directions, use the remainder theorem to find the remainder for the division. The remainder for the division is the function value at that root. So we would plug in the root 2 and show that that substitution and get 12. 12 is our remainder. That tells us, no, this is not a factor. In other words, I should say, no, x minus 2 is not a factor. I think that's a better way of saying it. So you understand, because we got a remainder of 2, or a remainder of 12, or a function value of 12 at 2, then x minus 2 is not a factor. That's what we need to see if we're asking if use the remainder theorem to find the remainder for the division, and then tell whether that is a factor of the polynomial. All right, let's do one more. So we have this, and it tells us they want to know from this division what the remainder is. They're not asking you to do the division, and this will tell us whether you're reading the directions or not. If you read those original directions, this looks like a division problem. It is not. All right, what it is saying is find p of 1, because 1 is our root. And so that means 2 times 1 cubed minus 3 times 1 squared plus 1. So that's just 2 minus 3 plus 1, which is 0. So there's the remainder. We use the remainder theorem to decide this. So this would be yes. X minus 1 is a factor. All right, again, you need to see the substitution and then your decision whether it's a factor. All right, so now what? Well, this was titled the remainder and factor theorem, so we kind of handled the remainder theorem and how we're going to use it. Now the factor theorem. The factor theorem says that the binomial x minus r is a factor of the polynomial if and only if. That's what IFF means, if you haven't seen that before. If and only if p of r equals 0. Well, we kind of knew that, didn't we? If we plug in a value into a function and we get 0, we know that's one of the roots, or zeros, right? So this has a pretty straightforward application. It says, is y plus 2 a factor of this? Well, for y plus 2 to be a factor of this, I can use this factor theorem to say, let's find, we'll just call it f of negative 2, because when I say y plus 2, the root is negative 2, right? R equals negative 2 here. So f of negative 2 would be negative of negative 2 to the 6th, right? Just using this function and plugging it in. Plus 4 times negative 2 to the 4th, plus 3 times negative 2 squared, plus 2 times negative 2. So this would be, let's see, 2 to the 6th is going to be positive, right? Negative 2 to the 6, I should say, is going to be positive, and that's going to be 64, and then we take the opposite of it. So negative 64 plus 2 to the 4th. 2 to the 4th is 16. Again, negative 2 to the 4th would also be 16, because it's an even power of that negative, so it comes out positive. So 16 times 4 is 64 again. And then plus 3 times negative 2 squared is positive 4. So that's plus 12. And then minus 4. So these cancel, leaving us 12 minus 4, or 8. So is it a factor? It's asking. Because of this, we can say no, not a factor. Using the factor theorem to make that decision, right? It's not a factor. Because if it was 0, we would know it's a factor. But it didn't give us 0, so it's not a factor. All right. Another question from this section. Find the binomial factors for x cubed plus x squared minus 5x minus 5. Well, now we got a whole different type of problem. How am I going to find the binomial factors of this? This is really similar to what we did in 4.1. They're asking you essentially to find all the roots, because if I find the roots, I can find the factors, right? When they say this factor thing, all right, it's going to basically be telling you we need to find roots. So we need our graphing calculator. So I'm going to bring that up real quickly. And there we go. And bring you back here with the calculator. We've got this equation, x cubed plus x squared minus 5x minus 5. So let's put that in our calculator. Let's go to y equals, clear this out, and do x raised to the third plus x squared. Again, you could try factoring this, but we might be able to do grouping here, but I think it's easier just to look at the graph first and see if I see anything that's obvious. So let's do that. Let's do zoom 6 and see what we get here. See if we see something. It looks like at least one good one at -1. Let's look at the table. Second table, and I don't see anything there. Looks like -1, like I said. -1, there's one. It's the only one I see is -1, right? So we know right now, just from looking at this, that we have one root at x equals -1. That gives us a factor of x plus 1. So right now, we know x plus 1 is one of our solutions. What that means is if x plus 1 is a factor, we can factor it out of here. In other words, divide it out. So let's do that division. We got 1, 1, -5, -5. And if I put -1 in the box here, we can do this. So bring down the 1, multiply by -1, add, I get 0, multiply, I get 0, add, I get -5, multiply by -1, I get 5, add, I get 0. I know I should have got 0, just like in 4.1. If we didn't get 0, probably multiplied wrong or did the graph wrong, or divided wrong, I should say, or did the graph wrong. So what is our quotient that's left? Right now, we know that we could rewrite this polynomial as x plus 1 times, let's see, what is this? This is x squared minus 5, right? No x term, so it's that. So we've got our binomial factors. We're done. Because these are both binomials, aren't they? There's nothing else left. There's two binomials. We could solve for it, but it didn't ask us that. Again, this is going to be very important. You read the question in this chapter more than ever. It says find the binomial factors. Binomial factors look like this, right? Binomial means two-term polynomials. These are two-term polynomials. This, whoops, is our solution. X plus 1 times x squared minus 5. Those are our two binomial factors. That's all we have. All right, it's not asking for your solutions. All right, all we're looking for, there was no solution to this. It was just a polynomial. We're just looking for the binomial factors. All right. So let's do another one. This one, x cubed plus x squared minus 4x minus 4. Again, we could go to the graphing calculator and find it, but I want to revisit one type of factoring that you may not have seen for a little while. So just kind of bear with me. There was a type of factoring we called grouping. if I group these two, and I take something out of them, if I can factor this part, I can factor this part by taking an x squared out. They both have an x squared term, and it would leave me x plus 1. Here, I can factor a -4 out of both of these, and it would leave me an x plus 1. If these two are the same, by grouping, I can write this as x squared minus 4 times x plus 1, and that's it. Whoops. Because by distributive property, if x squared times this minus 4 times this is the same as saying x squared minus 4 times that. All right, so we've got this. Now, this is a little different than the last one. If you go back here, technically, I could have factored this because it is a difference, and it would have been x minus root 5 and x plus root 5. But I don't expect you to go to roots on this. But for something like this one, I do want you to be able to show me you understand that x squared minus 4 can be factored itself as x minus 2 and x plus 2 times x plus 1. If we get nice, clean binomial factors, I want to see those. All right. So these would be our 3 binomial factors. Again, I kind of showed that, but I didn't say it. I would have also accepted for this answer x plus root 5 and x minus root 5 using difference of perfect squares. But this isn't a perfect square, so I don't assume you're going to do this. All right, this first answer would have been fine. The perfect squares like this, I expect you to be able to factor those. All right, and that's it, guys. If we're looking for binomial factors, this is all I need, is these pieces. All right, you can also have gone to on this one particular one, you could have gone to the graph and found the roots. If we found the roots for this, when on the graph, you would have seen 2, -2, and -1 as the roots. We could have used those to create our binomial factors. So we're kind of using what we did in 4.1 for an extension in 4.3. We find roots. Given roots, we can find factors. Again, I want you to have very clear in your mind the difference between those. These are the factors that would be created from the roots. X equals 2, -2, and -1, right? These are the roots. These are the factors. They're asking us for the factors in this section most often. All right, but finding the roots gives you the factors. That's it, guys. That's what we're doing in this section. And we will, again, extend this in our next unit. So make sure you practice this, ask questions tomorrow, all that good stuff, and have a wonderful day.